Hello and welcome to Night Science Stories. Tonight we will travel back through deep time to an era when our world may have worn a shell of ice from pole to pole for tens of millions of years. It sounds impossible, yet the clues sleep inside ancient stones, waiting for a calm mind and a curious ear. Close your eyes if you wish and picture Earth as a pale blue lantern wrapped in white glass, and ask a simple question with a very human heartbeat beneath it. If the planet froze, how did life continue to breathe, to feed, and to dream of tomorrow? Imagine standing on a silent shore beneath a sky the color of polished steel. Sea ice stretches to the horizon like a frozen plain. Wind moves over it with a soft hiss, carrying the dry whisper of snow crystals drifting like dust. The sun is low and weak, a coin of light behind thin cloud. The ocean is not open water, but a lid of ice that could be many hundreds of meters thick in some places, scored and rough, with occasional cracks that exhale little clouds of vapor. The land is not the green of forests, but a mosaic of rock and ice, with rare dark outcrops where wind has scoured down to the bedrock. In this quiet and austere world, there is still motion. Glaciers creep, snow falls. The ocean beneath the ice continues to flow, dense and cold, carrying salt and dissolved gases. Darkness rests upon the planet, but it is not a lifeless darkness. It is a darkness like a long night that will eventually give way to morning. To understand how Earth might have entered such an extreme state, we need to step back to the chapters before the freeze, into the late Proterozoic time. Picture the continents fused and unfused across long spans of time, the crust moving on the slow conveyor belt of plate tectonics. During this era, a supercontinent called Rodinia existed. The arrangement of land controlled the path of ocean currents and the geography of deserts and rains. The atmosphere carried greenhouse gases such as carbon dioxide and methane, which trapped heat and kept surface temperatures within the narrow comfort zone that allowed liquid water to persist. This balance was delicate. Volcanic eruptions added carbon dioxide. Growing mountain ranges exposed fresh rock that pulled carbon dioxide from the air through chemical weathering. The oceans absorbed gases and later released them. Life itself was already at work. Tiny cells floating in the sea, taking in carbon dioxide, giving back oxygen, building fragile shells, forming mats of microbes that trapped sediment in sticky layers. The climate system was a chorus of many voices, not a single solo line, and sometimes in deep time that chorus can shift from harmony to a runaway crescendo. One of the most important players in this ancient drama is something simple. Ice is bright. When sunlight strikes a white surface, much of that light is reflected back to space rather than absorbed. This reflectivity is called albedo. A small growth of ice increases albedo a little, which cools the surface a little. More cooling allows more ice to form. More ice means more reflection, and more reflection means further cooling. This is a positive feedback loop. In a mild world, this loop is limited by the dark surfaces that remain exposed, such as open ocean and dark rock. But if ice begins to advance into the bright equatorial zone where sunlight is strongest, the feedback can strengthen. White ice in the tropics reflects a great deal of energy. The cooling deepens. If enough of the planet becomes covered, the albedo feedback can tip Earth into a global ice state. Once there, The high reflectivity keeps the world cold, even if the sun shines day after day, because so much of that energy is bounced back into space. If albedo is one hand on the climate dial, chemical weathering is another. The outer skin of continents is not inert. Rainwater contains dissolved carbon dioxide, which forms a weak acid. That acid reacts with silicate minerals in rocks. The chemistry transforms carbon dioxide gas into dissolved bicarbonate that rivers carry to the sea, where it can be locked up for long spans of time in carbonate minerals. This long, slow chemical factory acts as a thermostat on geological timescales. When Earth warms, rainfall and the speed of chemical reactions increase, which removes more carbon dioxide and nudges temperatures down. When Earth cools, weathering slows, allowing volcanic carbon dioxide to build back up. During the run-up to a global freeze, this thermostat appears to have been pushed out of its usual range. Something made weathering very efficient at sucking greenhouse gas from the air, while volcanic additions could not keep pace. The stage was set for a long slide into cold. What could have pushed the thermostat so far? The shape of continents matters. As Rodinia fragmented, large stretches of land may have migrated toward the equator. In the tropics, sunlight powers heavy rainfall. Warm rain, persistent storms, and lush chemical reactions on fresh rock can strip carbon dioxide from the atmosphere far more rapidly than cold and dry high latitudes can. Imagine long mountain chains straddling the equator, their young rocks full of minerals eager to react with water and carbon dioxide. Now add monsoon-style rains powered by strong solar heating. Rivers would rush toward the sea, hauling weathered ions that once were greenhouse gas. Over hundreds of thousands of years, this persistent drawdown could thin the warm blanket of carbon dioxide. With a thinner blanket, nights become colder and winters longer. Glaciers begin to find footholds even at lower latitudes. The white advance strengthens albedo. The feedback does the rest. There is another ingredient that likely helped. Fresh volcanic rock is chemically hungry. When a flood of basalt pours out of deep fissures to make a large igneous province, it creates a landscape of dark, glassy, easily weathered material. Rain on basalt is like rain on thirsty soil. The chemical reactions that remove carbon dioxide proceed quickly. Young mountain belts offer similar fresh surfaces. As the crust is uplifted and fractured, new mineral faces are exposed to air and water. The combined effect of widespread basaltic plains and new mountains could have been a global appetite for carbon dioxide that exceeded what volcanoes and metamorphic degassing could replace. The atmosphere thinned in terms of greenhouse strength, and the planet began to lose heat to the cold of space. Over this stage of Earth history, the Sun also offered less warmth than it does today. The star that sustains us brightens very slowly over billions of years as fusion in its core changes its internal structure. In the late Proterozoic, the Sun was dimmer by several percent compared to the present era. A few percent may sound small, but spread across the vastness of a planetary disk, it is a significant reduction in energy. A planet with fewer greenhouse gases, more reflective ice, and a slightly fainter sun is a planet where winter can gain ground and not easily retreat. In such a world, the line between open water and sea ice can creep toward the equator, and the high clouds that once warmed the ocean can thin. The long night begins to settle. For many years, geologists were cautious about the idea that glaciers reached the tropics. The very notion seemed to conflict with intuition. Tropical regions are the warm belts of the planet today. How could ice ever cover them? The answer is carved into stones that formed near ancient sea levels and low latitudes. Some sedimentary layers that were once tropical contain rocks that typically form beneath glaciers. At first, the observation felt like a paradox. Then more clues were found in many places, on multiple continents that were far apart even in ancient reconstructions. Slowly, piece by piece, the weight of evidence grew. If we walk into the field with a geologist as our guide, we can look for a distinctive collection of features left by moving ice and by ice rafts. Tillites are hard rocks formed from glacial till, which is the mixed jumble a glacier leaves behind when it melts. A tillite often contains a chaotic blend of clay, sand, pebbles, and large stones, all pressed together by the weight of new sediments above. Dropstones are another sign. Imagine a boulder frozen into the base of a floating chunk of ice. That ice drifts out over the sea and melts. The boulder falls like a slow stone meteor into soft marine mud and deforms the layers. When the mud becomes rock, you can still see the boulder and the drape of disturbed laminations around it. Glacial striations are scratches on bedrock carved by stones at the base of a glacier as it slides. When you find these features inside layers that were deposited close to the equator, the conclusion is startling. Ice had reached the warm belt of the planet. How do we know those layers were indeed near the equator when they formed? Paleomagnetism is a quiet and patient tool that reads the memory of ancient magnetic fields recorded by tiny iron-rich minerals as they crystallize or as they settle in sediment. When a lava flow cools, minerals such as magnetite can align with the direction of the magnetic field. When fine sediments settle in still water, their microscopic magnetic grains can slowly rotate into alignment before they are locked into place. Later, skilled scientists measure these directions very carefully and correct for the tilting and deformation that rocks have suffered over long time. From those data, they can estimate the latitude at which the rock formed. This is not a simple task, and it is always accompanied by uncertainty that must be handled with care. But across many sites and many studies, a pattern emerged. Some of the glacial deposits formed at low latitudes. The ice had traveled far, far from the poles, perhaps even to sea level near the equator. Now let us return to the big picture and to our gentle guiding question. If Earth became a snowbound world for tens of millions of years, how did life survive? The answer is not a single refuge, but a tapestry of refuges stitched together across sea and land. Beneath the ice, the ocean did not stand still. Salt water can remain liquid at temperatures below the freezing point of fresh water. Geothermal heat from within the planet rises through the crust and into the seafloor. Along mid-ocean ridges and at submarine volcanoes, hot fluids rich in minerals pour into the dark sea. There, communities of microbes live by chemosynthesis, using chemical energy rather than sunlight. Over those communities, animals gather. They do not depend on photosynthesis directly. They depend on chemistry and on the steady exhalation of heat and compounds from the interior of Earth. Even far from volcanic vents, the deep ocean circulates. Nutrients and dissolved gases continue to move. The ice overhead is a barrier to wind and to much of the exchange with the atmosphere, but it is not an absolute barrier to life below. Within and beneath sea ice, microscopic habitats exist. Brine channels are tiny, branching veins where salty water remains liquid, even in bitter cold. In those microspaces, microbes can live, cycling nutrients in slow motion. On the surface of ice and on cold rocks, dust and fragments of organic matter collect in dark patches called cryoconite. In modern polar regions, cryoconite can host small communities of microbes and algae. In an ancient global ice state, similar microenvironments could have provided little islands of life, each modest but significant when multiplied across an entire planet. On land, not all areas would be equal. Volcanoes on continents release heat that can melt snow and ice around vents. Warm springs can open pools of liquid water in very cold landscapes. Subglacial lakes can form beneath thick ice sheets, where pressure and geothermal heat combine to keep water liquid. In such lakes, life today can persist in darkness. In the past, similar places might have sheltered microbial ecosystems for long spans of time. Even at the surface, temporary openings in sea ice called polyneas can appear where winds or currents keep water exposed. Those windows allow limited exchange of gases with the air and a faint trickle of sunlight, enough perhaps for a thin ribbon of photosynthetic life during rare, gentle seasons. If life sheltered what finally brought the morning, what warmed the world again, the same thermostat that helped set the freeze would set the thaw. With vast ice covering much of the continents, chemical weathering slowed to a near halt. Frigid and dry conditions reduce rain. Ice shields rock from the acid work of water. Meanwhile, volcanoes continue to breathe carbon dioxide into the air, very slowly but relentlessly. With weathering suppressed, greenhouse gas accumulates. Year after year, century after century, the veil thickens. The sun is still dimmer than it is today, but a dense blanket of carbon dioxide and perhaps methane can trap heat quite effectively. Eventually, the greenhouse forcing reaches a threshold where tropical ice begins to melt during the warmest season. Dark, wet surfaces appear, absorbing more light. The albedo feedback works in reverse. More absorbed energy melts more ice, which darkens more area, which absorbs yet more energy. The lid opens. Open ocean appears across great distances. Storms awaken. Water vapor increases in the atmosphere, which itself is a greenhouse gas. The planet enters a dramatic deglaciation. As ice retreats, weathering restarts with a rush. Freshly ground rock flour from beneath the ice meets rain and river. The chemistry draws carbon dioxide down again. The climate slides back toward a more temperate state. Oceans that were capped for a long time mix deeply, bringing nutrients to the sunlit zone. Photosynthetic life enjoys a pulse of productivity. Over long time, ecosystems reorganize. In later chapters of Earth history, this cycling of extreme cold and warm aftermath may have set the stage for new experiments in complexity among living things, but that is a later tale. For now, we remain within the first act of the story, where ice taught the world the power of reflectivity, and rocks taught the world the quiet force of chemistry. Let us drift back and revisit each element slowly with the patient tempo that helps the mind rest. Reflect on how a bright surface can change the destiny of a planet. A simple snowfield at low latitude carries far more consequence than the same patch near a pole because it sits under stronger sunlight. The equatorial sun is a steady drumbeat of energy. Dress that band of Earth in white and you send a great share of that energy back to space. The planet cools. A thin margin separates a comfortable climate from a slippery slope into deep freeze. Consider again the long dance between volcanic exhalation and the chemical appetite of rock. The planet breathes out through volcanoes. The land breathes in through weathering. When continents are arranged so that their most reactive margins lie in rainy belts, the inhalation can overwhelm the exhalation. Warm rain falls on fresh basalt or on newly lifted silicate rock. Rivers carry dissolved bicarbonate to the sea. On the seabed, minerals form that store carbon for spans of time longer than human imagination can easily grasp. This is not a fast process on a human clock, yet over a few million years it can shift the composition of the air enough to matter. Now, picture the slow drift of continents. Rodinia, the old supercontinent, comes apart into large fragments. Those fragments wander toward low latitudes. Ocean currents reorganize. Coastlines lengthen in the tropics, where storm tracks are strong. Monsoon systems tighten their grip. In the lab of the open sky, hot rain runs across rock day after day. The atmosphere is subtly edited. The page of climate is rewritten in quiet strokes that add up. Layered upon all this is the sun, young and not yet at full strength in the late Proterozoic. Even a small decrease in solar luminosity can tip the balance when greenhouse protection thins. If you have ever stood near a window on a winter morning and felt the difference when a cloud slides across the sun, you have sensed a tiny version of this effect. Earth felt it over continents and oceans as wide as imagination. When geologists first read the rocks and whispered that tropical ice might have existed, they faced skepticism. That resistance was healthy. Extraordinary claims require extraordinary tests. Those tests came from many directions. Dropstones in what were once low-latitude seas, striations that point to moving ice where warm water should have ruled, tillites laid down not in polar silence but near ancient tropical shorelines, paleomagnetic signals measured from grain after tiny grain, aligned like compass needles frozen in time. Each line of evidence has its own uncertainties and its own loud and quiet notes. When you place them together on the staff, a melody appears. It tells of ice that walked into the sun. Throughout this long frozen chapter, life kept to its work. Microbes at vents took nourishment from chemical gradients. In brine channels, cells traded molecules in that cramped liquid architecture. In subglacial lakes, communities evolved to live in permanent night as ice retreated and waters mixed. These survivors expanded. Evolution doesn't sleep. It proceeds even in the dark, guided by selection and chance. Traits that help survival in cold and low light become common. Then, as light returns, a different set of traits finds favor. This back and forth is part of why our planet is so rich in forms and strategies. Hard times prune, good times branch. There is a gentle lesson in all this that suits a quiet evening. Planets are not fragile in the way a glass is fragile. They do not shatter, they change state. They find a new balance for a while and then another. Life, tiny yet persistent, finds refuges, discovers new chemistries, and waits for openings. Our world has known climates far stranger than anything recorded by people. Through all of it, the ocean has rolled on, exchanging heat, salt, and stories. The land has lifted and worn down. The air has thickened and thinned, and over it all the sun has slowly brightened. a patient star that sends enough light to keep water liquid and to warm a thin skin of atmosphere, where birds now fly and where you are listening tonight. As you rest, picture that bright white earth one last time. See the long, glowing crack of a new lead in the sea ice. The word lead here means an opening of water, not the heavy metal, and it meanders like a river across the frozen plain. Steam rises softly as cold, dry air meets newly open water. Above the lead, the sky shows a faint blue, as if hinting at a warmer day to come. In that narrow lane of water, tiny cells drift and divide. They do not know the global story, they only live it. The morning arrives slowly in geological time, yet it arrives. When we think about how Earth could freeze into a global ice state and why life was not extinguished, we are invited to hold two ideas at once. The first is that planetary systems can amplify small changes into great shifts. Bright ice, fresh rock, warm rain, and a slightly fainter sun together can rearrange climate on a scale that seems astonishing. The second is that life is stubborn and resourceful. Give it a little liquid water, a little energy, and some chemistry, and it will make a home in the depths of a vent, in the veins of brine within ice, beneath a kilometer of glacier where heat from the interior keeps a secret lake liquid. On the first day of a gentle thaw, in a dark melt pond that looks up at a pale sun. If you are drifting toward sleep now, let the details fade into a soft blur. Remember only the outline, a world bright and cold, a mirror that returned sunlight to space, rocks that sipped carbon from the sky, continents that wandered into the rain belt, volcanoes that kept breathing out their slow, warm fog of carbon dioxide until the weight of that fog opened the ice. Evidence etched into stones carried from a quiet tropical sea and later lifted into the light of day for people to read. Scientists leaning close to tiny magnetic grains to learn latitudes of ancient shores, and always the ocean moving beneath the lid, a quiet engine that sustained life while the surface slept. Before we close, hold in your thoughts the calm confidence that comes from understanding. The Earth is old beyond measure. It has endured extremes we can barely picture, and yet it remains a place of rivers and forests and birds and people telling stories in the night. The idea of a planet-wide ice cover is not a tale of doom. It is a tale of resilience, of feedbacks and balances, and of the persistence of life even when the sun is faint and the wind is sharp. The same deep processes that carried the world into cold carried it back toward warmth. The same oceans that hid life beneath ice later lit the fuse for a new burst of diversity. This is not only geology, it is a lullaby written in stone. Thank you for listening. May the slow rhythm of deep time soothe your thoughts as you rest. Tomorrow, when you wake, the present will feel a little larger because you have wandered through a chapter that few imagine in detail. If at some point tonight you pictured a white earth and then watched the first dark lead of open water appear, you have walked beside the patient forces that shape worlds. Let your breathing fall into an easy cadence, and let sleep come as gently as a snowflake on silent ice. There is a quiet argument playing out in the scientific imagination. In one scene, the planet is locked in a hard shell of ice, with sea ice stretching from pole to pole and reaching even the equator. In the other scene, the planet is cold, but not completely sealed. Bands of thin ice or patches of open water persist in the tropics, enough to let light enter and let winds breathe across the sea. These are the two main visions that researchers debate when they picture a deeply frozen Earth. One vision is the snowball idea. The other is the slush ball idea. The first is elegant and absolute. The second is nuanced and ragged around the edges. Both try to honor the same set of clues, and both can be drawn in a way that fits the story told by ancient rocks. If the world had truly worn a hard shell, the ice in the tropics might have been many tens or even hundreds of meters thick. That thickness would make sea ice more like a ceiling than a skin. It would crowd out waves and muffle storms. It would cut sunlight to a faint grey glow in only the shallowest cracks and thin places. The slush ball idea softens that picture. It says the planet could be nearly sealed, yet still allow narrow belts of thin ice or scattered lanes of open water near the equator. Those blue pathways, kept open by winds, tides, and persistent ocean currents, would become corridors where air and sea could trade gases, and where glimmers of daylight might sustain photosynthetic life for brief seasons. Climate models can be tuned to favor one picture or the other, depending on assumptions about snow cover, cloud behavior, and the way sea ice fractures under stress. Field evidence does not always discriminate cleanly between the two. Some deposits speak of ice at sea level in the tropics. Other clues hint that wind-driven waves once touched shallow tropical shores during the coldest times. This is not a courtroom, and there is no verdict. Instead, there is a slow and careful weighing of possibilities, and the planet that emerges from that weighing is both brutal and dynamic. Under either vision, one thing is nearly certain. The global ocean did not stop being an ocean. It became a dark and cold ocean with a thick lid, but below that lid, water still moved. Imagine a planet-wide sea capped by ice of uneven thickness. In some places, the ice could be as thin as a few meters. In other belts, it could be thicker than a city building is tall. Pressure ridges would arch like frozen dunes where plates of ice collided. Between those ridges, long lanes of open water could form when winds tore the pack apart. Oceanographers call these lanes leads, which in this case means an opening rather than the soft metal with the same spelling. Elsewhere, persistent winds or upwelling currents could prevent ice from forming, leaving polynyas, which are windows of open water surrounded by ice. These features exist today in polar seas. They allow exchanges of heat, gases, and moisture even in long winters. On a nearly sealed Earth, they would become lifelines. The ice itself is not a perfect barrier to light. Snow is bright and reflective, but sea ice that has been stretched and refrozen year after year can be patchy and translucent in places. Cracks let light pierce into the sea for a short distance. The quality of that light would be thin and blue, filtered by crystals and water, yet for some hardy microbes the minimal photon budget could still matter. Under a thick lid the ocean would stratify, the upper waters would be cold and salty, the deeper ocean would be cold as well, but its chemistry would take on a different character as oxygen became scarce and dissolved iron accumulated. Tides would continue to slosh because the moon still pulled on the sea. That tidal kneading would work the pack ice and keep the lid from becoming static. In this quiet, mechanical way, the system stayed alive. Far below, along ridges and faults, the interior of Earth kept pace with its own slow breathing. Hot fluids, rich in dissolved minerals, flowed out of cracks in the sea floor. Some vents were black smokers, roaring chimneys that belch water so hot it would flash to shimmering darkness as it met the cold ocean. Other vents were pale and alkaline, places where reactions in new crust produced hydrogen and methane. Around both types of vents, life could persist on chemical energy rather than light. Microbes can oxidize hydrogen or sulfide and use the released energy to fix carbon. This is chemosynthesis, a way of making food that does not depend on sunlight. Around the chimneys grow strange gardens even in our time, with tube worms, clams, and shrimp that harbor symbiotic bacteria. In the deep freeze of ancient times, these oases would have been even more important. They are not rare miracles. They are natural consequences of a planet with an active interior and a global ocean. Between the surface ice and the deep vents is a lattice of tiny rooms where life can also linger. When sea ice forms, it excludes salt. The expelled brine drains downward through networks of microscopic channels. These brine channels remain liquid at temperatures far below the freezing point of fresh water because they are intensely salty. In those thin spaces, microbes can lodge and exchange molecules at a pace that is slow but steady. Nutrients drift in, waste drifts out. The channels widen and shrink with the seasons. A world under a lid becomes a world of capillaries. In addition, wind carries dust and soot and fragments of organic matter onto the surface of snow and ice. In gentle sun, those dark specks warm slightly and melt tiny pits. The pits concentrate water and nutrients. They are called cryoconite holes. Today, polar cryoconite can host colonies of bacteria, algae, and simple animals that sleep through long, cold months and awaken in short summer light. Imagine similar pockets scattered across a white planet. Each pocket is small. Their combined area across global snowfields could still be significant. On land, the ice is not a dead weight. It flows downhill and scours rock. Where ice is thick enough, the pressure at the base can melt a thin film of water even if the air above is bitterly cold. That water can collect in basins, making lakes that never see daylight. Modern Antarctica hosts such lakes. Water enters and leaves through narrow channels beneath the ice, driven by pressure differences and the gradient of the bedrock. Microbes live there with no access to sunshine. They use chemicals delivered by percolating water that has touched crushed rock and carried its ions into the dark. Now, place volcanoes onto this white land. In regions where crustal plates meet and grind, magma rises. Some volcanoes erupt beneath ice and create flat-topped mountains. Others merely release heat and gases through fields of hot springs and fumaroles. Around those vents on a snowball Earth, there would be rings of bare ground, trickles of liquid water, and mats of microbes feeding on chemistry. These are oases of warmth in a global winter. To look for signatures of such an ocean and such a land, geologists read the mineral archive. One arresting clue comes from the return of banded iron formations long after they had faded from the rock record. For a large stretch of Earth history before the deep freeze, the oceans contained significant dissolved iron because the water was not fully oxygenated. When oxygen became more abundant in the sea, that iron tended to precipitate out, and the classic rhythmic stripes of iron-rich layers largely stopped forming. Then, during the chapters of deep glaciation, new banded iron formations appear again in some places. The likely explanation is that a sealed ocean became poor in oxygen once more. Under a lid, with little contact with the air and reduced photosynthesis at the surface, the deep water could accumulate iron in its soluble form. Later, when openings returned and oxygen again mixed into the sea, the iron precipitated in a broad pulse, painting the record with iron-rich layers that had been rare for a very long interval. It is as if the ocean had taken a deep, secret breath of iron and then exhaled suddenly when the lid lifted. Another startling set of rocks sits directly above many glacial deposits like a soft blanket thrown over a rough floor. These are the cap carbonates, layers of carbonate that were laid down rapidly once the ice retreated. They can be unusually thick for a short episode of deposition. They often contain needle-shaped crystals of aragonite and smooth-coated grains called pysoids that grew as rolling particles in energetic shallow water. In some places, there are ripple marks so large that a person standing beside them looks small. Those giant ripples tell of powerful currents and waves that may have been driven by a supercharged atmosphere during the first seasons after the thaw. The chemistry of the cap carbonates is also unusual. They carry carbon isotope signatures that point to a massive reorganization of the carbon cycle. In language meant for bedtime, you can think of these layers as the planet catching its breath after a long, cold hold. The release is sudden and exuberant, and the ocean scribbles its excited signature in stone. The isotope story deserves a gentle moment of attention. In the shells of ancient organisms and in the muds and crystals of old seas, there are variations in the ratio of carbon-13 to carbon-12. Scientists write this as delta 13C. When large amounts of organic carbon are buried or burned, the ratio in the ocean and the air can shift. During deep freeze events, there are sharp plunges in delta 13 degrees Celsius in some successions. Those plunges hint that the balance between carbon in the air, carbon dissolved in the ocean, and carbon locked in minerals and organic matter changed quickly and dramatically. At the same time, the ratio of strontium isotopes in marine minerals sometimes points to rapid weathering of fresh rock, which would make sense once ice ground mountains into powder and torrential post-glacial rains washed that powder to the sea. Sulfur isotopes and even rare signals like mass-independent fractionation can add their quiet voices to this choir, telling of episodes when the surface ocean lost oxygen and when bacteria that breathe sulfate took center stage in the deep. Put those chemical voices together with the physical evidence and a living picture begins to form. The deep freeze likely made the ocean poor in oxygen and rich in iron and other reduced compounds. Microbes that prefer such conditions would have flourished in the dark water. Methane-loving and methane-making microbes might have played important roles, especially near seafloor sources of hydrogen and in sediment below stagnant water. If the surface ocean at times became oxygen-poor, even in the sunlit layer, purple and green sulfur bacteria could have bloomed, using light and sulfide in a way that is exotic by modern open ocean standards. These conditions redraw the border between habitable and hostile waters. The boundary is not a hard line, but a shifting zone that depends on mixing, on the supply of nutrients, and on the pace at which oxygen is consumed. When the ice finally retreated, winds would have stirred the surface vigorously, Oxygen would have invaded and pushed those redox boundaries downward. Many organisms would have been stressed by this new chemistry. Many others would have found new opportunities. Now step back and let the whole climate machine run in your mind at a relaxed speed. Under a lid, chemical weathering on land slows almost to a pause because liquid water is scarce on bare rock and because the cold turns the usual rain-driven chemistry into a long nap. Volcanoes continue to exhale carbon dioxide. With little weathering to balance that exhalation, the greenhouse blanket thickens year after year. Clouds form over leads and polinias, but the global reflectivity remains high until a threshold is crossed. When the first significant areas of dark water appear and stay open through the warm season, more sunlight is absorbed. The ice begins to retreat in a positive feedback. Water vapor increases, and water vapor is itself a greenhouse gas. A supergreenhouse phase starts to build. This is not a hyperbole. It is a term the community uses for conditions when greenhouse warming is far stronger than anything today. Under those skies, storms would be intense, rains would be heavy, and the chemical appetite of fresh rock would be awakened across entire continents. Rivers would become loud with sediment. The sea, initially poor in oxygen, would soon be stirred and oxygenated, and the vast stock of dissolved iron would precipitate and settle. The supergreenhouse exit from the deep freeze may have been relatively swift on geological time. A world could have been locked for many millions of years and then warmed enough to lose much of its ice in only a small fraction of that time. The cap carbonates are the calling cards of that rapid change. They form when warm, carbon dioxide-rich water holds abundant dissolved carbonate and then suddenly becomes favorable for precipitation as pressure, temperature, and chemistry change together. Imagine a shallow tropical shelf that was just liberated from ice. The air above is heavy with greenhouse gases. The water is warm and oversaturated with respect to carbonate minerals. Wave action endlessly tosses grains and needles, and carpets of crystals grow almost as fast as they can be moved. Tides sculpt giant ripples across the new sea floor. Within a short span of time on the deep clock, a blanket several meters thick is laid down. That blanket rests directly on rocks scratched by ice. The contrast is astonishing and yet fully natural. During the first seasons after the thaw, acid rain may have fallen as that carbon-rich air met rain clouds. The chemistry would have etched fresh rock, especially on mountain slopes freshly polished by ice. This intense weathering would have pulled carbon dioxide back down out of the air over tens of thousands of years, a process that would gradually calm the supergreenhouse. In the meantime, the ocean, newly mixed and newly oxygenated, would have offered nutrients to the sunlit surface. Biological productivity could have surged, feeding a cascade through microbial communities to larger and more complex forms of life. This is one reason many researchers link the aftermath of deep glaciations to later evolutionary leaps. Stress prunes. Abundance lets branches form. When we return to the debate between a hard snowball and a slushy world, we can do so with a softer heart. The planet is complex. It can hold a little of each vision at the same time. Some intervals may have been closer to a hard seal, especially during the coldest peaks, with ice so thick that only the faintest light touched the top few meters of water. Other intervals may have been more perforated, with persistent open belts where winds and tides kept blue lanes alive. Over millions of years, the balance could have shifted as volcanoes waxed and waned, as continents crept a little farther into the tropics or drifted away, and as the sun slowly brightened. The rocks do not insist on a single unchanging picture. They invite us to recognize a system that oscillated near extremes. In the spaces within sea ice, the brine channels and the cryoconite pools illustrate how life writes small but legible notes to itself. Brine channels are like a dendritic river network made of liquid threads. Within those threads, salt-tolerant microbes form biofilms and exchange genetic material in a way that seems slow to us but is normal to them. The chemistry inside a channel varies from one end to the other. Oxygen may be high near a crack that admits a trace of air and low deep inside where microbes consume it. Nutrients may be concentrated by freezing and melting cycles. Viral particles and tiny grazers patrol the space, keeping populations in balance. Cryoconite holes, by contrast, are little ponds whose dark floors absorb sunlight. In the weak polar sun, they can become a few degrees warmer than the surrounding ice. They can host simple food webs. If you imagine a white landscape dotted with millions of such holes, you start to see how the surface of a planet can be both hostile and welcoming at the same time. Beneath continental ice, the subglacial realm is a continent of its own. There are valleys, hills, and basins. Water flows along the base, sometimes in broad sheets and sometimes in pressurized channels that can carve tunnels. Where the bedrock is crushed into fine powder, that rock flour enriches the water with minerals. Microbes in the dark use iron, sulfur, and other elements as part of their metabolism. When a subglacial lake forms, it can persist for a very long time if the geometry and the heat flow are favorable. The water in such a lake may be isolated from the atmosphere for hundreds of thousands of years or more, yet it is not sterile. It is a quiet laboratory where evolution proceeds in the absence of light. On a planet-wide ice world, thousands of such laboratories could have existed under the big ice sheets. Add to that the rings of hot ground around volcanic vents, and you have a quilt of refugees stitched across white continents. In the ocean beneath the lid, the redox story is as important as the temperature story. Redox is a short way of saying reduction and oxidation, which is the language of electron transfers in chemistry. When oxygen is scarce, iron and manganese remain in dissolved forms that are mobile. Sulfate can be reduced by bacteria to sulfide, which can then react with dissolved metals to make minerals like pyrite. Methane can build up where organic matter is broken down, in the absence of oxygen. When the surface ocean is oxygen poor, even in the light, special communities of bacteria that use light and sulfide can occupy the shallow layer. This is photic zone euxinia, a phrase that sounds complicated but simply means that even the sunlit upper ocean is anoxic and sulfidic. The return of oxygen during deglaciation would have driven dramatic changes. Iron would precipitate as iron oxides. Sulfide would be oxidized. Organisms adapted to low oxygen would either retreat to deeper layers or experience stress. The boundary of habitability would move quickly. The sulfur cycle during these times may have become a dominant partner with the carbon cycle. Under a lid with little oxygen, sulfate reduction can become a major pathway for microbial metabolism. The amount of sulfate available in the ocean depends on the weathering of continental rocks and on volcanic inputs. After the thaw, with intense weathering, sulfate levels could rise and then affect the kinds of microbes that succeed. The methane cycle also interacts. Methane made in sediments under ice could accumulate under the lid and be released when the lid lifts, adding to the greenhouse pulse. Then, with oxygen returning, methane would be oxidized and its atmospheric life would be short. These seesaws are part of the reason the chemical record is so lively across the end of deep freeze events. It helps to keep the timescales in mind without getting tangled in figures. The cold intervals likely lasted on the order of tens of millions of years, not simply a few winters multiplied many times. The warm exit may have been swift by comparison, perhaps on the scale of tens of thousands of years for the main transition, with longer tails of adjustment. The cap carbonates themselves can represent only a brief bloom of deposition. The iron-rich layers can represent a geologically punctual precipitation of dissolved supplies that built up over a long, dark wait. The isotope drops in delta 13C can be sharp in their onset and then recover as the system settles. These differences in tempo are part of what makes the rock record read like music, with slow drones and sudden cymbals. All of this may sound grand and dramatic, yet the tone of the planet during the cold time would have been quiet. Winds hissed over ice, snow grains skittered like sand. The ocean had no breaking waves in most places. It moved with the deep pulse of tides and the slow turn of the planet. Life whispered in brine threads, at vent chimneys, in subglacial caves, and along the edges of polynyas where air met water and a silver skin of frost formed each night. When the morning came, it would not have arrived everywhere at once. Long belts would have darkened and then widened as dark water absorbed sunshine and built heat. Storm tracks would have ignited along the new thermal gradients. Rain would have hammered newly exposed ground. Rivers would have carried the signatures of a transformed world back to the sea. The comparison of snowball and slushball scenarios invites one last reflection. Science often advances by holding competing pictures in the mind and letting evidence decide slowly. In this case, the competition may be less a sword fight and more a dance. During the deepest nights, the planet may have been nearly sealed. During the shoulder seasons of that long winter, the planet may have been slushy enough to keep tiny photosynthetic populations alive in the tropics. The biology of vents and brines and subglacial worlds would have persisted in either case. The chemistry of iron and sulfur would have written similar lines in stone. The cap carbonates and the isotope plunges would have followed the same broad script with different regional accents. From these chapters of ice and thaw, one practical understanding emerges. Earth systems contain feedbacks that can amplify small nudges into large outcomes, and they also contain stabilizers that eventually guide the system back toward a temperate state. Fresh rock acts as a silent broker for carbon. Sea ice acts as a mirror that can call winter down upon itself. Volcanoes act as a slow exhalation that you cannot stop. The sun brightens very slowly, which means that the same greenhouse blanket will warm more effectively in a later era than in an earlier one. When these actors share the stage in a particular arrangement, a snowball scene can unfold. When the arrangement changes, the curtain can rise on a warm and restless sea. The endurance of life through such extremes offers a second understanding. Survival does not always look like abundance. Sometimes it is a string of refuges, each small, each marginal, and each sufficient. A brine channel, a cryoconite pool, a lake beneath ice, a pale alkaline vent on a ridge, a narrow belt of open water where the wind refuses to let ice close. From 1,000 such refuges, the planet can reseed itself when conditions ease. The rock record tells us that after the deep freeze, complex life flourished. It does not tell us every detail of how the seed was kept alive, but it tells us enough to say that biology is patient and resourceful. As the super greenhouse retreat unfolded and the sky calmed, the continents would have greened in places that had been bare for ages, measured in millions of years. The shelves would have grown reefs and mats. The oceans would have layered with a more familiar pattern of oxygen-rich surface and darker deep water. The grand experiments in form that would later mark the Ediacaran seascapes and the Cambrian seas needed a platform. The exit from the snowball provided it. Chemical cycles rebooted, erosion reorganized landscapes, rivers found new paths, the climate settled into bands and seasons that allowed diversity to spread. The white shell did not end life. It sculpted the playing field on which later life would run. In closing this quiet walk through the middle of the story, picture once more the essential ingredients placed in a calm row. A planet with continents drifting toward the equator, fresh reactive rock under warm rains, greenhouse gases drawn down over long spans of time, bright ice advancing and reflecting sunlight away. A sun that was a little fainter than now, a lid of ice that transformed the ocean, the chemistry and the habitats of life, vents and brine channels and subglacial lakes that gave life shelter, a slow build-up of volcanic carbon dioxide, a threshold crossed, a rapid warming into a super greenhouse, torrential rains and giant waves on new shores, iron leaving the water and falling as rust-colored layers, carbonate blankets spread over scoured floors with giant ripples frozen into place, sharp dips in carbon isotopes that mark a world catching its breath, oxygen returning to surface waters and pushing redox boundaries downward. The borders of habitability drawn again in new places. Each element does not need a number to be vivid. Each element is a shape on a table that you can move with your thoughts. Together they form a picture that is both austere and hopeful. The snowball and the slushball are not enemies. They are different moods of the same old planet. The ocean under the lid is not a grave. It is a nursery lit from within. The deep freeze is not a permanent sentence. It is a long night that sets the stage for morning. The first rains after the great thaw were not gentle. They fell through air that carried a heavy load of carbon dioxide, and their drops were laced with weak carbonic acid. When this rain met freshly scraped rock on the rising flanks of young mountains, the chemical reaction was immediate and relentless. Minerals surrendered their cations to the water. Clay formed. Ions streamed into rivers that ran milky with rock flour ground by the retreating ice. The planet had been quietly charging a chemical battery during the long freeze, and now the circuit closed. This was hyper-weathering, a time when the normal balance between the breathing out of volcanoes and the breathing in of continents tilted sharply. Rains fell season after season, dissolving the edges of peaks and lifting the products of that dissolution toward the sea. In those first thousands of years after the lid of ice fractured, the speed of erosion and weathering would have seemed astonishing on a geological clock. Think of granite newly unveiled by retreating glaciers. Fractures from the pressure release opened tiny pathways for water. The acidic rain and runoff sought out feldspars and mafic minerals eager to react. River water swelled with calcium, magnesium, and bicarbonate. On continental shelves, warm seas saturated with dissolved carbonate invited the rapid growth of crusts and grains. The cap carbonates, those blankets that lie directly atop glacial debris in many places, are the mineral summary of this chemical rush. They formed quickly. Their textures are full of needles and oolites polished by vigorous waves. Their surfaces preserve giant wave ripples that look like frozen music. Each ripple is a line drawn by storms moving over seas that had been quiet for ages, measured in millions of years. Acid rain is an evocative phrase, but here it describes a natural part of the planetary thermostat. When the air holds a great deal of carbon dioxide, the droplets that form in clouds carry a dilute acid that reacts with silicate rocks. The reactions remove carbon dioxide from the atmosphere and send it into the ocean as dissolved bicarbonate, where it can later rest inside solid carbonate minerals. In the early days of the thaw, rainstorms could scour entire slopes and feed mud-laden torrents that braided across new floodplains. From time to time, cataclysmic outbursts would surge from subglacial reservoirs as warm air and warm water undermined ice dams. These sudden releases carved chutes and scablands, rearranged river courses, and delivered house-sized boulders into deltas in a single night. The planet was washing its face after a very long sleep, and it was not using a soft cloth. Weather and water do not act alone. Air currents reorganize when the skin of the world changes. A surface that shifts from high reflectivity to dark ocean absorbs far more solar energy. Sharp contrasts appear between cold lands still clinging to seasonal snow and newly opened seas that drink sunlight and exhale moisture. Such contrasts feed great storms. Towering anvils of cloud ride along temperature boundaries. Lightning stitches the sky. Rains come in long, wide bands. The phrase "storm of the century" would be a misfit here because the baseline itself is unfamiliar. Yet you can imagine systems so strong that they march across an infant ocean for days. Their winds piling water along coasts, their waves sculpting ripples that would later become stone. In newly deglaciated basins, meltwater lakes ringed by ice cliffs could fail when undercut by warmth, releasing floods that accelerated the delivery of nutrients and ions to the sea. Floods are not only destructive, they can be creative too. Where rivers reached the edge of the continental shelf, they fanned out and laid down thick layers of fresh sediment. These layers became homes for early ecosystems, reoccupying shallow seas. In channels, pebbles and cobbles tumbled and knocked the corners off each other until they became smooth and round, recording the force of moving water. In quiet bays, fine mud settled and laminated as seasonal rhythms returned, giving the rock record tidy pages that later eyes could read. The newly invigorated hydrologic cycle was rewriting the surface quickly, but it was also feeding the deep story of life that would unfold over the next tens of millions of years. It is a strange but recurring pattern that life often rebounds with creativity after a crisis. During the long freeze, eukaryotic cells that housed their genetic material within a nucleus had likely persisted in scattered refuges. Some were anchored to rocks near volcanic warmth, others drifted beneath the ice in brine filaments, and still others endured in subglacial lakes where chemistry rather than sunlight powered metabolism. When light, oxygen, and nutrient supply improved, these lineages found space and energy to explore. Eukaryotic cells tend to be larger than bacteria. They can build internal scaffolding, form temporary limbs, engulf food, and sometimes fuse with other cells in ways that speed innovation. Biomarkers preserved in old rocks hint that complex algae rose and diversified around the time of the late Neoproterozoic thaw. With more algae floating near the surface, the ocean food web gained new rungs. Grazers had more to eat. Predators found targets worth chasing. The tempo of ecological interaction quickened. Diversity begets more diversity when energy and nutrients are abundant. Another gentle boost to complexity came from the chemistry of phosphorus. During glaciation, ice had ground mountains into fine powder rich in phosphorus minerals. When the meltwater and the early rains flushed this powder into the ocean, a nutrient wave rolled across the shelves. Phosphorus is a throttle on biological productivity in many marine settings. A temporary surplus would have encouraged algal blooms and fueled the burial of organic matter. Burial of organic matter removes carbon from the short-term cycle and allows oxygen to accumulate in the air and water. This stepwise rise in oxygen was not smooth. Instead, it came in pulses as climate, erosion, and biology pushed and pulled each other. In the shallows, sponges and other simple animals may have found windows of time when oxygen levels crossed the minimum threshold needed for their metabolism. Those windows widened as weathering and burial continued. Soft-bodied animals left the faintest of footprints, but those faint clues are there. In the sediments of the Ediacaran period, which followed the last great Neoproterozoic glaciation, we find impressions of organisms that look like quilts of fronds and discs. Their exact relationships are still debated, yet their presence tells us that multicellular animals with organized bodies had appeared. Trace fossils also speak. These are not shells, but tracks and burrows, the signs of movement and of feeding within soft sediment. They suggest that some animals had a front and a back, and that those animals pushed into the mud searching for food or shelter. As oxygen pulses lengthened and strengthened, the variety of such traces grew, pointing toward a world in which animal behavior was becoming more complex and more common. The restoration of the coupled cycles of carbon and phosphorus took time because the initial surge of erosion gradually tapered. Once fresh reactive surfaces were consumed and soils stabilized with new life, the chemical throttle relaxed toward a more ordinary pace. Still, the system did not return to the exact state it had before the deep freeze. The arrangement of continents was different. The ocean circulation patterns had been rebuilt. The air held a different blend of gases. The biosphere had more players and more connections among them. The new balance allowed the upper ocean to maintain more consistent oxygenation, at least in wide bands along the continental margins. In those bands, carbonate platforms could grow steadily. Ecosystems could engineer their own environments, and food webs could climb to new levels of interaction. There is a suggestive thread that runs from the end of the snowball-like phases to the later Cambrian proliferation of animal body plans. No single cause can claim full credit for the Cambrian bloom, yet climate played the role of a careful stage manager. By drawing down carbon dioxide through intense weathering and by allowing oxygen to build through the burial of organic matter, the environment crossed thresholds that made mineralized skeletons and active lifestyles more practical. Calcium carbonate saturated seas favor the evolution of hard parts. Oxygen-rich surface waters support larger bodies and faster movements. An increase in the diversity and abundance of algae supports more energetic consumers. With each new adaptation, such as burrowing or predation, the community responds with its own innovations, such as defensive shells or rapid movement. This is an arms race written in gentle rhythms over millions of years. The concept of a global ice state in the late Neoproterozoic is not the first time Earth flirted with extremes of cold. In the Paleoproterozoic, more than 2 billion years before the present, the planet endured a series of extensive glaciations that may also have reached low latitudes. Those earlier events happened around the time of a profound shift in atmospheric chemistry, often called the Great Oxidation Event. Cyanobacteria had evolved the trick of splitting water with light, releasing oxygen as a byproduct. As oxygen accumulated, iron dissolved in the sea precipitated as rust-colored layers that taper off in frequency as the ocean changed character. The climate at that time may have been affected by the removal of methane, a powerful greenhouse gas, when oxygen first became common. The earlier snow-like episodes and the later Neoproterozoic ones are not identical, but they echo each other in the way feedbacks between life, air, ocean, and rock can draw the planet toward and away from the edges of habitability. This ancient perspective feeds a modern curiosity that looks outward. If planets can carry the scars and gifts of snowball experiences, might we recognize such worlds orbiting other stars? The instruments we aim at distant systems can measure how bright a planet appears and how that brightness changes as the planet rotates. A world with wide white belts near the equator would reflect light differently than a world with blue oceans and dark continents. Polarization of reflected light can, in principle, distinguish bright ice from cloud tops. Spectra of the air can reveal the presence of gases such as oxygen, methane, and carbon dioxide, and even hint at water vapor. No single measurement would shout snowball, yet a pattern could emerge. A cool spectrum with strong signatures of ice and very low water vapor, combined with a seasonal brightening that suggests expanding ice, would tell a story. If that same world later shows evidence of abundant water vapor and warmer temperatures, we might be catching it in the act of leaving a deep freeze. For life, the important part is not simply the cold or the warm, but the presence of liquid water somewhere and a source of energy. On an exoplanet, vents beneath ice could provide both. Back on Earth, the map of the deep freeze was uneven. Some regions wore caps of ice that were a kilometer thick or more. Others, especially along persistent wind belts near the equator, held lanes of open water, or at least thinner lids. Geography decides through a web of influences. Mountains intercept moist air and create strong snow shadows. Plateaus catch cold air and radiate it to space, lowering local temperatures and encouraging the growth of ice that then reinforces the cooling through reflectivity. Narrow seas line up with prevailing wind and tide in ways that open and maintain polynyas. Ocean currents bring relatively warm water from the deep to the surface, in some regions more than others. The way continents sat during the late Neoproterozoic placed long coastlines in tropical rains where weathering could run at high speed, and it also placed shallow basins in positions where they could be sealed by ice but still receive inputs from rivers when summers turned a little softer. In those regions where ice met the sea, the mechanics of glaciers governed daily life. Imagine a towering ice cliff where a grounded glacier reaches deep water. Under the action of tides and gentle swells, the cliff calves. Large slabs break away with sounds like thunder and become floating icebergs that carry stones frozen into their bellies. As these bergs drift, the stones grind, scratching grooves into any bedrock they visit, and when the bergs melt, the stones fall and bury themselves in soft sediment, making dropstone signatures that geologists later find. Beneath the grounded ice, pressurized rivers run along the bed and carry a heavy load of sediment. These subglacial rivers can make tunnel valleys and deposit long ridges of till called drumlins. In places where ice becomes thinner and floats, it forms shelves that extend over the sea. The bottoms of those shelves can develop keels and rills from melting and refreezing as currents move beneath them. The line where grounded ice becomes floating ice is called the grounding line, and its back and forth migrations decide how far the ice reaches and how much sediment a river can carry under it. When warmer water undercuts a shelf, the grounding line retreats. When cold returns or snow adds weight, the line can advance. The whole system is a humming machine built of frozen water. All of these processes produce marks in stone that survived the thaw. Grooves on rock outcrops run in consistent directions that show the paths of glaciers, till layers sit jumbled with stones of many sizes and many origins. Varves, which are pairs of thin layers that record annual cycles of sedimentation in glacial lakes, stack by the thousand, as regular as breathing. Giant current ripples made by fast, deep flows freeze into place on surfaces that were beaches for only a brief window after the thaw. Cap carbonates lie flat and bright above the rough older layers like a calm sea over a stormy one. Banded iron formations return for a short encore and then recede again as oxygen claims the deep ocean. Carbon isotope ratios plunge and then recover in a pattern seen in different places on different continents. It is a harmony of clues. The post-glacial weather, though harsh at first, settled into patterns that encouraged the spread of life. Thick storms gradually learned to move along set tracks. The contrast between warm sea and cool land softened. Rains became more seasonal. Deltas built and stabilized. Coral-like organisms that could extract carbonate from water made frameworks that calmed waves. Microbial mats carpeted tidal flats. In such settings, the first animal builders of hard parts found both material and calm water. They turned chemistry into architecture and left shells that have survived to be catalogued in drawers and painted in field notebooks. The arc from deep freeze to flourishing is not a story of a single switch flipped once. It is a sequence of thresholds crossed with pauses between them and with local advances and retreats that differ from place to place. The important thing for the resting mind is the pattern. Feedbacks can push a system toward a stark state. Those same feedbacks, captured by a different balance of inputs, can help bring a system back to a gentler condition. The Earth system has this resilience built in. It is not an invitation to complacency in our own time, but it is a quiet reassurance that the planet has moved through wide swings and still carried life forward. When you picture that early world in your thoughts now, try to see it both as a set of processes and as an atmosphere, a mood. Grey skies bright with tall clouds, a sea that goes from black and smooth to a deep blue with whitecaps as the lid breaks and the wind can finally run. Mountains that weep clay and send it into newborn bays. Rivers that find their mouths anew and write fresh deltas. Oceans that begin to breathe again. In that air, oxygen that was once rare arrives and lingers. In that water, phosphorus that was once trapped in stone becomes food. In that light, algae make sugar and small animals begin to stir in the mud. The story is scientific, but it is also soothing because it reassures us that long nights end, that the morning can be bright, and that life uses every pause and every pulse to invent new ways to be alive. The ocean never surrendered entirely to ice. 3 quiet sources of resilience kept it from freezing to the last drop. The first was the steady warmth rising from within the planet. Even when the surface lay under a white shell, the interior continued to breathe heat through the crust. That geothermal flow is not dramatic like a volcano, yet spread across the vast sea floor it adds up, a background glow that keeps deep water just a little above the final threshold of solidification. The second source was the tug of the moon and the sun. Tides flexed the ice and kneaded the sea beneath, stirring layers and preventing the water from resting long enough to freeze completely. That rhythmic motion also cracked the ice, opening narrow corridors and thin places that released heat to the sky and then drew in fresh ocean water to be warmed from below. The third source was salt. Seawater doesn't freeze at the same temperature as pure water. Its salts depress the freezing point, and when sea ice did form, it rejected brine into slender veins that stayed liquid even in severe cold. Together, geothermal warmth, tidal motion and salinity created a safety margin so that the ocean remained a patient, circulating heart under its icy skin. Imagine that hidden heart. At mid-depth, a slow river of water flowed along density layers shaped by salt and cold. On the bottom, young crust along ridges leaked hot fluids, and older crust still shared a gentle warmth. The result was an ocean that could never quite sit still. Even when winter claimed the surface world for ages measured in millions of years, the interior of the sea held enough energy and enough motion to avoid the absolute stillness that turns water to stone. Yet life needs more than liquid. Life, at least the life that makes food from light, also needs photons. Under a planetary lid, light was precious. Snow is brilliant and throws sunlight back to space, but sea ice that has aged and refrozen many times can grow translucent in places, and cracks and thin spots, shifted open by tides and wind, become windows. Through those windows, a scant trickle of blue light sank into the upper ocean. It was not plentiful. It might have been hundreds of times weaker than the light on a modern summer day, but for some algae, the smallest allowance is enough. These hardy cells can harvest scattered photons and stretch them across long hours, using efficient pigments to fill their simple sugar factories. They do not aim for speed. they aim for survival. Light also arrived from living bodies. In the deep, some microbes and small animals glow. Their bioluminescence is not a flood of brightness, but the pulses and soft waves of living light may have mattered indirectly. They attract attention, guide movement, and structure nighttime behavior, even in a world that is already dim. Near the underside of ice, communities adapted to pale illumination could graze and drift in a rhythm set by tides, and by the thin daily cycle of twilight pressing through snow. The physics of light under ice is a subtle art. Snow scatters photons strongly, turning direct beams into a diffuse glow. Thick ice absorbs red light more readily and allows blue to wander farther. Any dust that settles on the surface darkens a patch, warms it in the weak sun, and opens small melt pools. These shallow basins connect with channels in the ice and make tiny skylights. In modern polar seas, filamentous algae cling to the ice underside near such skylights and grow in stringy curtains. Picture similar curtains along ancient fracture lines, living slowly, feeding the first steps in food webs that would expand when the lid finally thinned, while light and warmth whispered at the top and bottom of the ocean. The arrangement of continents and the choreography of currents wrote the larger weather. Tectonic drift had carried broad land masses toward the equator in the time leading up to the deep freeze. Land in the tropics changes climate in two important ways. First, it brightens the band under the strongest sunlight because rock and seasonal snow reflect more energy than open water. Second, it strengthens chemical weathering where warm rain is common and mountains are young, drawing carbon dioxide from the air. The ocean responded. With continents aligned like stone breakwaters, currents looped into new patterns. Some narrow gateways channeled flow like a river through a canyon, creating upwelling zones that brought cold water toward the surface. Other passages closed, ending warm exchanges between basins. The complete pattern favored a cooler world. When the ice later spread, the same geography helped it hold. Currents themselves carried memories. A cold surface makes cold and salty water where sea ice forms. That heavy water sinks and spreads along the bottom. In a near snowball state, such bottom waters could remain very cold for a very long time, reinforcing the lid from below. When continents block or guide that bottom flow, they can lock chill into basins as surely as a dam locks water into a lake. Only when greenhouse warmth rebuilt in the air would the pattern shift and allow deeper mixing to erode the ice from underneath. No great idea in earth science lives without argument, and the vision of a global ice planet is no exception. Some geologists question whether ice truly reached sea level in the tropics. They point out that in regions of tall mountains near the equator, glaciers could have carved the land and dropped stones into nearby seas without the entire planet being sealed. Others emphasize the challenge of keeping a world covered in ice for tens of millions of years, given volcanic emissions of greenhouse gases. Climate modelers note that clouds, dust, and sea spray can change reflectivity and insulation in ways that are hard to capture fully. The cap carbonates that sit above glacial layers are sometimes interpreted differently from place to place. Are they the product of a sudden warm world ocean oversaturated with carbonate, or are they simply the work of local seas rising across coastal plains? New findings continue to shape the picture. Paleomagnetic signals from ancient lavas and sediments have been remeasured with better tools and better corrections for the slow tilting and folding of rocks through time. Many still point to low latitudes at the time of ice deposition. Dropstones and striated pavements have been found in layers that geologists map as near ancient shorelines. Banded iron formations that were rare for long intervals reappear in direct association with glacial deposits and then vanish again above the cap carbonates. Carbon isotope profiles plunge in similar ways in different basins around the world. None of these clues alone demands a fully sealed planet. Together, they make the snowball vision compelling to many. For those who wish to see the evidence with their own eyes, the planet has left a generous field guide. In the desert ranges of Namibia, pale cliffs hold thick cap carbonates resting on dark glacial debris. The Flinders Ranges of South Australia display sweeping outcrops where glacial layers and their carbonate blankets are stacked like chapters in a book you can read while walking. In the Canadian Cordillera and farther north in the Mackenzie Mountains, the Rapitan Group and related units record glacial deposits mingled with iron-rich formations. In the Svalbard archipelago and across parts of Norway and Scotland, polished pavements and striated bedrock appear below sediments that imply a marine setting. In the Yangtze region of China, the Nantuo Formation and its overlying carbonates tell a similar story in a different accent. Even in the American Southwest, in Death Valley, and nearby ranges, ancient layers record a cold sea that lapped a shoreline long vanished. Standing in any of these places with a hand on the stone, a person can imagine the hush of snow on an alien Earth. To understand such an alien climate, researchers build numerical worlds. They begin with simple energy balance models that treat the planet like a sphere of zones, each balancing sunlight in and infrared energy out, with ice and clouds changing how much energy is reflected. They step up to general circulation models that simulate winds, storms, and currents. Those require choices. What is the reflectivity of snow that has aged under a pale sun? What fraction of cloud droplets form ice crystals when airborne dust is scarce? How easily does sea ice fracture when it is thick and under tidal stress? How much carbon dioxide was present in the air before the freeze? How bright was the sun in that era? What were the orbits and the tilt of the planet with respect to that sun? For each parameter there is an uncertainty. Scientists explore these choices with ensembles of runs, comparing model outcomes to constraints from rocks. If a model world produces equatorial ice and then places thick carbonate blankets directly on top of glacial debris after a greenhouse buildup, it earns attention. If it cannot, it is tuned again or set aside. As minds rest on these ancient chapters, it is natural to wonder what a new chapter of global ice would do to the world of people. The short answer is that a true return to a hard snowball state is extremely unlikely in the near future. The sun is brighter now than it was in the late Proterozoic. Human activities have increased greenhouse gases in the air. Tectonic arrangements are different, yet exploring the scenario helps us understand resilience. If long-sustained cooling began for any reason, the first changes would be the advance of seasonal snow lines and the longer hold of sea ice. Shipping lanes would close. Croplands at high latitudes would shorten their season. Infrastructure built for soft winters would groan under persistent frost. Water would become locked in growing ice sheets and sea levels would fall, exposing continental shelves. Human societies would adapt by shifting agriculture, by developing energy sources that do not depend on fragile supply lines, and by fortifying coastal cities against new storm tracks. Geothermal heat, already one of the quiet engines of a snowball ocean, would become a valued resource on land as well. Nuclear fission and, one day perhaps, fusion would offer steady warmth and electricity. A network of greenhouses and enclosed farms could keep food flowing. Long-distance trade would rely on rail and air routes redesigned for winter. None of this would be easy. Much of it would be possible. Civilization carries its own form of geothermal persistence. It is good to remember the unlikeliness of such an extreme, and at the same time to keep in view the deep flexibility that life on this planet has always displayed. To measure the age of rocks that carry these stories, geologists turn to clocks that tick in atoms. Uranium decays to lead through a chain of steps that proceed at a pace set by the inner structure of the nucleus. The half-life is measured in hundreds of millions of years, long enough to span these chapters without running down. When zircon crystals grow in cooling magma, they can incorporate uranium into their lattice, but reject lead. Any lead found inside later is the product of radioactive decay. By comparing the amount of uranium to the amount of lead and by cross-checking two independent uranium lead systems, scientists can assign ages with remarkable precision. Other minerals carry clocks based on samarium and neodymium, or rubidium and strontium. Magnetic minerals, aligned when lava cools or when sediments settle, record the direction of the planetary field and contribute to paleomagnetic maps that give ancient latitude. Stromatolites, which are layered structures built by microbial mats, offer a different kind of timekeeping. Their presence and style in certain layers help mark ecological context and, along with fossils of algae and simple animals, add a biological calendar to the physical and chemical ones. When all these clocks are read together, the story stops being a blur and gains chapters and paragraphs. The story of the snowball idea itself has chapters. Early explorers of ancient terrains noticed unsettling combinations of features. There were boulders dropped into quiet marine muds. There were scratches on rocks that looked like the work of moving ice, but were found in places thought to be ancient tropics. For a long time, these were curiosities, local puzzles to be solved with local explanations such as nearby mountains. In the 20th century, theorists studying the balance between sunlight and reflection realized that if ice advanced far enough toward the equator, a runaway feedback could make the planet leap into a much colder state. Energy balance models by researchers whose names are now part of the literature showed how the threshold could be crossed and how difficult it would be to reverse without a buildup of greenhouse gases. Later, field campaigns on several continents found more and more signs that low-latitude ice had indeed visited shallow seas. With the arrival of detailed isotopic records and better radiometric dates, the pieces fell into a narrative that many, though not all, accept. The idea continues to evolve as new data and new models sharpen the picture. Place these strands together and step back. A planet that entered a state of global cold for roughly 60 million years did not die. It retreated into a slower rhythm. The ocean remained a moving heart, warmed softly from below and kneaded by tides. The skin of the planet grew bright and reflective, and the sky thinned of greenhouse gases as warm rains earlier had scrubbed them from the air. Under the lid, life learned to live in brine veins, in dark lakes, beneath ice, and at chimneys where the interior met the sea. When volcanoes, patient and tireless, exhaled enough carbon dioxide, the balance tipped the other way. The lid fractured, winds awoke, storms drew giant ripples in new shallow seas. Iron fell from water that had hoarded it in the dark. Carbonate blankets formed quickly in warm, oversaturated seas. Oxygen pulses widened, and soft animals left faint tracks in mud. The cycles of carbon and phosphorus regained their stride. Food webs grew taller. In the long quiet after the thaw, the stage was set for the dramatic flowering of forms that would decorate the Cambrian seas. The lessons are calm. Feedbacks can take small nudges and make them large. Yet the same system contains paths back toward temperate balance. Life is fragile in the small sense and resilient in the large sense. A world can wear many faces and still carry the pulse of water and the whisper of metabolism. When we read stones from Namibia and Australia, from China and Canada, from Norway and the far islands of the Arctic, we are reading pages from a single book written by sunlight, salt, ice, rock, and time. It is a book that invites contemplation more than argument, a book that says the planet has endured and learned. Let these images settle like snowflakes, a blue heart beating beneath white glass, curtains of algae sipping a ghostly light, brine threads that glow with slow chemistry, a tide that keeps time beneath a silent surface. Mountains washed by strong rain as the first warm seasons return, giant ripples in shallow seas that hardened into stone, iron-rich waters exhaling their burden, carbonate crystals knitting blankets over rough ground, simple animals stirring in oxygenated shallows, clocks inside crystals telling us when each scene was staged. The idea of a snowball world growing from a puzzle into a story. As your breathing slows, allow the planet itself to become a lullaby. The long night was not an ending. It was a rehearsal for complexity, a deep breath before a long exhale. In that breath, the earth proved it could hold life close, even when the sun was faint and the mirror of ice was wide. From that proof came confidence, and from confidence came invention. The oceans that once slept under ice would later cradle coral reefs, kelp forests, and wandering whales. The continents that once wore white shields would later bear forests and fields and cities where stories are told in the evening. The same physics, the same chemistry, the same patient geology that once wrapped the world in cold also taught it how to wake. Thank you for traveling through the deep past with a calm mind. May these slow processes and gentle images carry you toward rest. When you close your eyes, picture the blue heart of the ocean still moving under quiet ice. Picture the first narrow lanes of water blooming in faint light, and know that mornings return even after very long nights. Sleep well.